Hey everyone, in the final video of this little lecture series, I would like to take some time to talk about algebraic vector arithmetic. So in the last video we talked about what it means geometrically to do arithmetic with vectors. We talked about vector addition, scalar multiplication, and then vector subtraction, which is kind of a combination of the two. And what we'd like to do now is talk about how we can add, subtract, scalar multiply vectors by not having to actually draw them, right? Because everything that we did geometrically, we had to draw the vectors. So let me just remind us here. We had vectors, say, v, with a hat always, right? A vector w. And if we wanted to add these together, what we did was we put tip to tail. We made a decision, right, about one of them going first. So this will be v plus w. And then we connected them like this. And we said that the sum is this vector right here, this resultant vector right here. This is perfectly fine geometrically to understand what it means to add two vectors, but it is not very good for actually computing with vectors. So from now on, what we're going to do is we're going to consider that we're in the vector space V3. You should be able to reduce all of this to V2, the vector space V2, very easily. And let's assume that all vectors are in standard position here. So remember what standard position means. This means that our vectors, if we were to plot them, their initial point would be at the origin. So here's x, y, and z. And so two vectors that are, in some sense similar to the ones we just drew, well, I'll call this w. We'll stick with red for w. Very different, I guess, than the one that we just drew. But there's w. Call this one v. We want to try to add these together. But these are in, like I said, standard position. So what does it mean? Well, it means that v in particular, we can write its standard coordinates here, its component form, x1, y1, z1, and we can do the same up here for w. So w, that one's going to be, let's call it x2, y2, z2. And remember, these angle brackets tell us that these are the coordinates, x1, y1, z1, x2, y2, z2, of the terminal points of these vectors. And the initial point is the origin, right? The angle brackets tell us both parts. Now we want to try to add these together. So, as we know, what we have to do is pick up this vector, w, and kind of parallel translate it, which we're allowed to do, over to here. And then the sum of these two is going to be the vector, which connects our initial point, which, look, because of the way we set this up, our initial point is the origin. So our resultant vector, by the way we set this up, v plus w, is in standard position as well, right? And so the question is now, we want to go from the origin out the blue vector v, and then out the blue vector, or the red vector w, to get to this new terminal point. And so what do we have to do? Well, this one, remember, has coordinates x2, or component form, x2, y2, z2. And if we want to get to this new green x-coordinate, we start at the origin, we go out x1, and then from x1 we pick up and we go out x2 more. So what do we have to do? We go x1 and x2, we have to add those together, right? So the component form of v plus w, this vector addition, we get by adding component by component, we add the components. So x1 plus x2. Same for the y direction, right? We go out y1 on the blue one, go y2 more on the red one, right? So we add them up. y1 plus y2, and then z1 plus z2. So vector addition is done by component-wise addition. All right, let's think about, so this is our vector addition, right? So this is how we can compute. It's very, very, very straightforward. So let's now talk about, again, let me label this, vector addition. The other operation we have is scalar multiplication. These are the only two operations that we have, right? So our scalar multiplication, remember how this works. Again, I'm going to put the vector in standard position, okay? So here's our x, y, z axes. Let's say, I'm just going to use, so let's say we have this vector v, again, standard coordinates, right? Standard position, x1, y1, z1. And this time I want to multiply by 2. So I want to do, let's do it in magenta. I want to find coordinates for 2v. Well, 2 is a whole number, so we know exactly how to do it. But we also know the geometry of this. We should be able to stretch this thing out, right? And this vector is 2v. And so what do we want to do? Well, we want to go twice as far in the x direction, twice as far in the y direction, twice as far in the z direction, right? And altogether, what's it going to be? It's going to be 2 times our component vector, x1, y1, z1, and then this 2 can distribute in some sense. It can distribute to each component. So scalar multiplication has to be done component by component. Vector addition is done component by component. So everything is done component-wise. All right, so here we go. If we wanted to do this in general, remember that our generic symbol for a scalar, we used alpha. So alpha v in general is going to be alpha times our component form. And like I said, this is going to distribute and be done component by component. So alpha x1, alpha y1, and then alpha z1. All right, and so this is our scalar multiplication done component-wise. So all operations essentially. So by the way, we set this up geometrically. We understand what it's doing, and then the formulas just come out. They're so nice, right? It's just some nice, easy formulas here for us to work with. So all operations, though, are component-wise. This means component by component, right? Component by component. If you have 2-dimensional vectors, 3-dimensional, 4-dimensional, etc., it works the same way. Now, let's do one more thing. I wanted to keep this video short because the last couple of videos have been a little longer than I would like. But let's suppose we have a vector v, and instead, so let's say its component form is this. So I will write the component form. x1, y1, z1. And let's remember that we can write this in ijk form as x1i plus y1j plus z1k. And then let's suppose we have another vector. So w, which again in component form is x2, y2, z2. It's got to be different, right? And this one in its ijk form will be x2i plus y2j plus z2k. Now I want to add these together. So I want to do v plus w, but I want to use the ijk standard unit vector form over here. So what am I doing? I'm going to add x1i plus y1j plus z1k. That's all one thing. It's all one vector. Plus then x2i plus y2j plus z2k. All right, and I'm going to add these up, and look what I can do. The I is like a like term, right? It's a vector. It's a unit vector, though. It's not a variable. We know exactly what it is. Same thing with the j's, right? J's are like terms. Same thing with the k's. The k's are a like term. All right, and so what we can do then is go through and group these by like terms. So we can say, all right, how many i's do we have? Well, we have x1 plus x2. x1 plus x2i plus what's the next term? Well, we have y1 plus y2 all times j. So now we're just using basic algebra rules, right? Then we have z1 plus, again, z2. Doesn't look like a 2. That's a 2. K. All right? And look what we've done. We add component by component I. Component by component j. Component by component k. And altogether, if you want to convert this back to standard form from its ijk form, you get exactly the same formula as what we got up above. All right? So x1 plus x2, y1 plus y2, z1 plus z2. There's the component form for vector addition. Scalar multiplication, I recommend, so let's call this a recommended exercise. All right, so write out scalar multiplication. So alpha times v in ijk form. I think you're going to find that it actually makes a lot of sense. All right, ijk form. All right, I'm going to leave this lecture here. Try that, and please enjoy.